Okay, so today, like I just said, it's the pre-lab for lab 5, flame test and atomic spectra. So tomorrow you're gonna get to visualize flame test. It'd be really pretty. And fun and interesting, but there is also math, so we're gonna go over the math today. So, anybody ever seen fireworks? Yes, awesome, 4th of July, spectacular. Anybody ever look at meteor showers or look at stars through a microscope, through a telescope? Awesome. So chemistry underlies all the colors that you see in fireworks and in stars, which is pretty cool. So the way that we'll talk today and you'll see tomorrow how we can use different elements on the periodic table to generate different colors, and how we can look at the colors, and that will tell us something about the underlying chemistry. So this is, again, we're going to have a million periodic tables. This is another periodic table, and it's color coded by a color that these metals exhibit when they're subjected to heat. So we've got yellows and reds and greens and blues. And so all of these specific colors, these metals are associated with a specific color. And there's a couple others that are on there. This is specifically a periodic table of firework colors. You can go to this website down here and look up more. Some elements are in there to provide heat energy, chemical energy, because we do need heat for this. Metals are like a little bit boring when they're in their solid state, but when we heat them up, that's when they generate these flames of beautiful colors. Okay, so the learning objective for today and for tomorrow. Okay, I guess it doesn't want to do a little bullet. So you're gonna tomorrow perform a flame test and absorb the characteristic colors of metal cations. So we haven't quite gone over charged atoms, cations, and anions, but we'll talk more about that this week and next week. But basically, when we heat up metals, cations, they have a positive charge, they emit a color. You're gonna be able to calculate the frequency and energy of emitted photons, explain the cause and effect of electrons transitioning between higher and lower energy level states, and be able to write the electron configurations. And also, like I said, you have this periodic table to check them. Any questions so far? We'll go into more of these. Okay, so has everyone seen like a spectrum like this before of visible light? Like the RGB, you know what RGB is, you've had some art classes. This is over like the red, orange, yellow, green, blue, violet. These are the main colors in the spectrum. And they have a wavelength. So visible light is an example of electromagnetic radiation. So if you hear electromagnetic radiation, just think light. And so the colors of light have a corresponding wavelength. And does anybody see this symbol right here? It's like lambda. It's a symbol. I have to search for it. So this is our symbol for wavelength. We're gonna remember this later on, but this symbol lambda, we're gonna see that in our equations. But violet light is a wavelength of 400 nanometers. Blue-green has a wavelength of 500 nanometers. Yellow-orange, 600 nanometers, and red, 700. So we'll look at a flame test and be able to associate that color of the flame with the wavelength. And so this is so we talked about how when we draw our nucleus, and then we have these rings where our electrons live. If an electron is here and you give it heat, it can jump to a higher state. So when an atom or an ion absorbs energy, its electrons can transition from a lower energy to a higher energy. This is a higher energy, and this is a lower energy. And so if you give it heat, it can jump to a higher level because it needs energy to get to a higher energy level. And so they can absorb heat from a flame, or heat from electrical energy or from other sources of energy, like chemical reactions, but energy is needed to make this transition. Then when electrons go back down to their lower state, they release energy, typically in the form of light. And this light is what gives us this color. So this is what is shown here. A ground state where it typically is, you give it heat or energy, it becomes excited. When it descends, it emits light. So this is like the theoretical and practical basis for our experiment tomorrow. Any questions so far? Okay, so the spacing, yes. Oh, yes.
So it's about like something a few slides back.
Okay.
When you were showing us the elements, like what color they glow.
Yes.
A couple of them were like black. How's that?
They give off a black color. They can also, so there's two things. So we're not going to go into fireworks. I was going to try to like go past a little bit. So carbon, like it is black when you burn it. But they can also be used as like an accelerant, like rocket fuel, jet fuel. You can add like just because. So if you want fireworks to show, if you're like making a black firework in the middle of the night, like no one will see it. But you can still include things that release heat to generate the repulsion for your things. So it's not going to make a pretty color, but they mix them in there to provide more chemical energy to make the other things explode. Yeah. So like it's that those three elements aren't going to make a pretty firework, but they are helpful for generating energy. Excellent question. Okay, I don't know why bullets don't show up, but that's okay. Okay, so this is where we were. So there's lots of rings. We talked about there's multiple energy states. So if one electron goes from the first ring out to the third ring, that requires more energy to make this transition, and more energy is released when it goes back down. And so this is an image that shows how the spacing between energy levels in an atom determines the size of transition that can occur, and thus the energy of the wavelengths and photons emitted. So if something starts, if its ground state is 2, and it absorbs this much energy, if it goes from shell 6 all the way down to shell 2, it's going to release 410 nanometers. If it goes from 5 to 2, that's a lower energy, so 430. 4 to 2 is even less energy, 486 nanometers. 3 to 2 is even less energy, 656. So the more distant, like the more spacing between the energy levels, the greater the energy release. And so it's kind of like reciprocal. So bigger distance, shorter wavelength, shorter distance, larger wavelength. So shorter transition red, higher transition violet. So the color that is emitted tells us something about how much energy was released. Okay, and so if we had, there are tools to measure every single color and every single wavelength that is emitted. These are called emission spectra. And so like helium, we have helium, oxygen, neon, argon, and xenon. They all have unique emission atomic spectra, like a fingerprint. So they're not just emitting, it's not just one electron that's being excited and then being released, the color being released. There are lots of electrons that move from different energy levels, which each electron moving to a different energy level is going to give a different spectra. And these are characteristic for each element. So we aren't going to do this, but this is something, oh, I probably could have already passed this out. I'll pass it out in a minute, but this is included in your pre-lab reading. Okay, so the flame test, I think it's in this part here. Yeah. So for instance, if you take a metal and put it over a flame. This is a Bunsen burner. What's VA? Barium emits a green spectra. So all of those little wavelengths combined give one color. So barium emits green, and SR is strontium, it emits red. So this is a known fact. People have done this before. So if I were up here and I were to put an unknown metal on a flame and it made it red, what would be a good guess? Awesome. So this is what we're going to be doing. Cool. So this this handout here has, so the pre-lab assignment, we'll get to working on that in a minute. And then this description right here, this is kind of what are on the slide. The procedure, what I'm talking about this here is on the slides that I'm going over. So when you read this, it should make more sense because I just elaborate on it a little bit. And then there's a procedure, and then there's a report at the end, and the report at the end is what you'll turn in. Okay, but if you want to follow along with the procedure, you're welcome to. Okay, so there are two critical equations. I thought, yes, this is why I put a star on this page. So there's two equations. This is the first one, and you can write them in your notepad. You might also want to write them on that conversion sheet, which has equations, because you're going to need to know this one and the other one. So there is a relationship between wavelength, frequency, and speed. And electromagnetic waves travel at the speed of light. And recalling the speed of light is a constant because it never changes, right? A constant, never changing. So C is equal to the speed of light. And we can look this up. Constants you can look up, they're known. Speed of light is 2.998 times 10 to the 8 meters per second. So again, this is something, the speed of light and this formula that we're about to write out are something I would probably put on that conversion sheet, or at least write in your notebook and draw a big square around it. Okay, so the speed of light is equal to the frequency, the wavelength. This is that lambda that we showed you, GTH. Times the frequency, and frequency is V here. And our wavelength is in meters, and our frequency is in inverse seconds. Second, -1, sorry. So if you're given this equation, C equals lambda times V, or wavelength times velocity, you know you can look up C as the speed of light. So we can always look this up, what constants are. So you'll be given one of these and you can solve for the other one. Anybody still writing that equation down? Okay. Awesome. Good to go? Okay. So there's one more equation that we're going to use, and we're going to use both of these and combine. You need both to solve most of the questions for this experiment. And they have one thing in common. So this one, I feel like this one is on your sheet already. This one describes the energy per photon. So photon energy, so E always stands for energy. And we give energy in joules. Is equal to a constant, and it's called Planck's constant, times the frequency. And so Planck's constant is in joules per second, so joules per second. And frequency is this inverse seconds. Sorry. This is gonna be joules times seconds. So this one is joules times seconds. This one is inverse seconds. So if we multiply those two together, the seconds are gonna cross out and we just get joules. And so Planck's constant, we know this, we can look it up, it's on your sheet, 6.626 times 10 to the negative 34 joule seconds. So what are our two constants in these two equations? Planck's and the speed of light. So if anytime you're given these two equations, remember you can look those two constants up. So the question might not give it to you, but it is a known thing. And what is common in both of these equations? V or frequency. So if you start with this equation and you solve for frequency, then you can move over to this equation. So like if you know wavelength and frequency, if you know frequency, you can solve this equation. And then once you know frequency, you can solve for wavelength. Question, yes, or comment?
Just a comment. So you guys have been dealing with two-step equations a lot now. I don't know if you guys have noticed the pattern in the class. The class really challenges you guys to use two different equations to solve for variables, right? So, and this is kind of like the next section. We just got done using in our specific heat lab. We were using Q equals MC delta T, and those variables to solve. So these are now our new formulas, and look out for problems that ask you to use both of these equations to solve for one of the variables. So kind of get used to seeing two-step equations or two-step problems in this class.
Awesome. Yeah, the big indicator in here that you need two equations or which two equations to go together is that they have some variable in common. So both of these have frequency in common. Okay. So we'll do one practice together. Okay. So what is the frequency and energy of blue light? So this could be a question. You need to solve for frequency and energy. That's kind of a key there that you're going to need two equations. Because with one equation, if you have two missing variables, you're not going to be able to solve for both of them. You need to be able to solve for one and then solve for the other. So blue light has a wavelength between 380 and 500 nanometers. So we'll just pick one kind of randomly to represent it. And like 440 is in the middle. So we could rewrite this. What is the frequency and energy of blue light of wavelength 400 nanometers? I think it's not going to work. Okay, so how would we solve this equation? How would we solve this problem? Yes.
Light equals the wavelength times sorry, 2.998 equals 440 times 8.
Equals 440 meters. Is it nanometers? 440 nanometers times V. Awesome. So start out, get your equations. We also, one thing you'll notice, so our answer, our speed of light is in meters and our wavelength is in nanometers. Yeah, I know, fun. So we will have to convert. You can do this over on the side somewhere. 440 nanometers. How do we convert nanometers to meters? Awesome. How many nanometers are in 1 meter? A lot. So what's 440 divided by 1 times 10 to the 9? -7? We'll see in just a minute. So. Okay, so instead of 440 nanometers right here, we'll put 4.40 times 10 to the -7 meters. Okay, and then we can solve for velocity. What's 2.998 times 10 to the 8 divided by 4.4 times 10 to the -7? (2.998 times 10 to the 8 divided by 4.40 times 10 to the -7? Nope, you're gonna divide it. So basically, this is multiplication. So frequency times velocity is multiplication. So we're gonna divide, so V equals, I'll write it out.
Is, frequency, right?
Yes,
And lambda is wavelength?
yes. Frequency is inverse seconds and wavelength is in meters. So our meters will cancel out and we'll just be left with inverse seconds. This M over S is the same as M times S -1. We've got inverse seconds. So what was this? Did anybody solve for this yet? So I've got, so a couple things to know. I've got my equation. I filled in my equation. I solved for it, and then I've written my answer
It should be to the
with the
14.
units. So the 14?
Yeah.
Awesome. Thank you. Okay. So now we have a frequency. So this is the frequency, 6.81 times 10 to the 14th inverse seconds. Now the next step is to solve for energy. Now we're using this equation. Okay, so we don't know what energy is, but energy is equal to Planck's constant times the frequency. That's our frequency. So we plug it in over here. This is inverse seconds. So these seconds are going to cancel with those inverse seconds. And what is 6.626 times 10 to the, oh yeah, -34 times 6.8 times 10 to the 14. Yes, you have a question or you have an answer? Yes. Okay, so the other way, okay, so speed is measured in seconds, like you ran 60 seconds long. Frequency is the inverse of that. So the other way to write so this is speed. So frequency is the inverse. Okay, or like 1 over S or S to the -1. Those are the two ways to write it. So it's equivalent to 1 over S. So like anything divided by 1 is the same thing. So if I divide speed by 1, you get the same answer. Then if we flip that to get the reciprocal, it's 1 over S. And that's kind of hard to write in formulas, so we typically write to the -1. So when you, so now, because, so I could write S -1, or I could write 1 over S. And if you multiply S by 1 over S, they cancel out. So like 6 divided by 6 is 1. Yes. Because, so the other way, so the speed of light is meters per second. So meters per second. And so when you cross out the m's, you're left with 1 over S or inverse S. So you could, instead of writing it like that, you could write it. That just looks a little silly. Yes.
Because that's how many waves are happening for every single second, right? That's why it's seconds inverse, because it's asking you
Per second.
this wave. Imagine something moving 10 to the 14th waves in a single second. That's an incredible amount of waves. That's the frequency of these waves. You're getting, trillions of waves every single second with this packet of light or whatever it is. Might not be light.
So the per second, it tells you that it's going to be like an inverse or 1 over. Those are excellent questions. Thank you. Any other questions, confusions? Yes, you have the answer. Beautiful.
I have 4.51 times 10 to the -19 joules.
Beautiful. Okay. So we were given one thing, 400 nanometers. We found our equations. We needed 2 equations. We converted nanometers to meters. Then we solve for frequency, and then we solve for energy. Awesome. Was that clear how that works out? Yes?
But now, there's
No, this is the answer. You would write. Well, so I asked you what's the frequency and what's the energy. That was the energy. This was the frequency. Usually the question won't ask you to figure out the frequency. It will just ask you to give energy, but you have to solve for frequency first. Because, yeah. If you're given wavelength, and you need energy, there is no equation that has wavelength in it. There is an equation with frequency. So to get to frequency, use this equation. That's why they're 2-step. It's like you can't get to the answer in 1 step. You need 2 different equations. 2-step equation. So let's see if I got, so for this question, I wrote down you need 2 equations. The first one you can rewrite it, which we did rewrite it when we were calculating it. For 440 nanometers is indeed 4.40 times 10 to the -7 meters. And then our frequency is indeed 6.8 times 10 to the 14th inverse seconds. So when you write this S to the -1, it means inverse. It means 1 over S. So it means per second, not seconds. Just think per second. 6.8 times 10 to the 14 waves per second. And then we solve for energy. Oh, I got a slightly different number, but that's okay. Maybe we use a slightly different intermediate. Oh yeah, I used 6.8, not 6.81. And we got roughly 4 point something times 10 to the -19 joule. Awesome. Everybody's cool with that? Sweet. Okay. So you have the handout. You can also find it on Canvas under our modules. It also comes from a similar textbook like ours. So if you lose your printout, you can go to Canvas and find it. And then we'll come back to that in a minute. Let's.
For a walk. Okay? I'm taking a walk with my family. So I have my 3-year-old daughter, I'm holding her hand, and we're taking a walk. And I'm walking like this. Okay? I'm taking a walk. What are my steps equal to? If we're looking at our speed of light equation in this analogy, my steps, would they be equal? Well, if I'm taking really quick steps, that's my frequency, right? But if I'm taking really big steps, that's my what? Wavelength. So who is going to have a bigger wavelength, me or my daughter? We're walking together. Me, because I have really long legs compared to her. So my wavelength is higher, but we're moving the same speed. So our C variable is the same. Just like all light moves at the same speed. Okay, just like me and my daughter are moving at the same speed as we're walking. So in order for my daughter to keep up with me, what does she have to do? Step faster. She has to do really, really quick steps because she has really small legs. So her legs are going really, really fast, and mine are like giant legs. Okay? So, who's using more energy to walk? Me or my daughter? Yeah, she's taking a ton of steps. So it's the same way with our wavelength. So the shorter your wavelength, the smaller your steps. That means you have to take a really, really high amount of steps every second to keep up with the same speed. So that question, if we go back to that question, okay, it asks you which type of wave has higher energy. Well, which type of wave has shorter wavelength? Visible light or UV? UV. So which one has higher energy? UV. It's just taking a ton of steps to go the same speed. Okay, so that's the analogy we need to think of. Think of you walking with someone that's a lot taller or shorter than you. Okay, so the shorter your wavelength, the higher your energy. And that's why things like X-rays, you don't want to just like sit underneath an X-ray machine all day because it's pumping out a lot of these high energy waves. And that can damage your DNA, cause cancer, all sorts of stuff like that. Even more so if we have a gamma ray, that's even higher energy. That's what gets released in like a nuclear explosion. Okay, so that's how you think about energy and waves. Who's taking the shorter step? Whoever's taking the shorter step is higher energy. Okay, that's it. You guys go back.
Awesome.
Oh, yeah. After we get.
Okay, so I put a couple things up on Canvas. So if you go to the modules tab, last week we pretty much only talked about atoms in the periodic table. All the recordings are under there. There is also a YouTube channel. This is what I was saying under week 4, this very first item, chapter 2 review, that is a scanned in PDF of all of your contributions. So thank you for sharing. Mr. Toms didn't fill one out, but I put a link on the home page to a 7-minute video that goes over the same thing of how to like go across the periodic table. And then if you look at the syllabus, if you click on the syllabus tab, I've updated the syllabus. I moved the schedule up to the top. And so every day that there was a syllabus like planned out for the whole year. And like when we update it, so you can go back to this and you're like, what do we do on the 10th? I don't remember. You can go look and it'll be there. Okay, tomorrow, what I want to do tomorrow is tomorrow is your lab. So you're gonna get to look at cool colors, colorful chemistry. On Friday, what I want to do instead of diving into new material is I'm going to review like the homeworks that y'all have submitted. Okay? Because some of you are doing great and some of you are doing good and some of you are making some mistakes. And I kind of want to go over what great looks like and what good looks like. And then I want to solve some equations so that people who aren't understanding them will be able to understand them moving forward. And so, like, for instance, a couple things that make grading easier and that help me help you are that one, anytime you're given a problem, you always write the equation. And then you show your work, and then the answer should always have a unit. And if it asks for scientific notation, it should look like this. And so those are kind of Like, I'm like, okay, there's some people that I don't want to count off points over points over points because I think I made some assumptions before we started. And I just want to make sure that going forward, that y'all kind of know what my expectations are for the homework. So I'll just go over homework in the next class and I'll give you time to finish any other homework and we'll do some assignments together so that I can see that you're getting it. Does that make sense? So like a big homework review Friday. And then that's why I didn't give you any homework this week. Because I was like, oh, I don't want the same people to keep making the same mistakes. So we're just gonna go over it, so you, hopefully you won't make those same mistakes in the future. There will be a quiz though. Okay, take it away, Kyle.
Okay, so, while I'm out next week and the week after, you guys might have a gizmo. Dr. Harris and I need to talk about this, maybe.
But this is also, yeah, we'll do that
We'll
today.
discuss that, but I want to show you guys how to get on there. So can everyone get their Chromebooks out, please?
Oh, do you need this or no?
Yeah. Yo,
Would it be a bio like last year?
it's similar. Okay, so I can give Dr. Harris, I made like a little screen recording of how to log on there, so I can give that to Dr. Harris so we can include it in any assignment with a gizmo. But I want to show you guys in case I'm not here so everyone can do it. So everyone go to Gizmos, just type that into Google. And then it's the very first link here. How much time do I have?
You got 7 minutes.
Oh, sweet. Okay, it's really important you guys don't get ahead of me here. This is where everyone always makes the mistake. So everyone go to login. You don't need to sign up or anything. You're going to go login. And then you're going to click student login. Okay, where it says student login, everyone has the same student login ID. If you guys could all write this down somewhere, like in your notebooks, on a piece of paper, somewhere. Everyone's student login ID is my classroom, which is K Toms. Everyone's going to type in K Toms for their login ID. No, all lowercase. Okay. Then you're going to click there. And you see two class options. You guys aren't in my biology class. You know that. You're in my college chem class. So you're going to click on P3 Chem 100. You guys with me still? Okay, then you're going to find your name. So all you guys should be in the system now. So if I am, who's not here today? Yell out if you're not here.
Adrian.
Where is it? Oh yeah, Adrian. Oh, there's Adrian. Okay, so I'm Adrian. Select your product. You guys all just have one product, which is Gizmos. And then it's going to ask for your passcode. Most of you guys, there's going to be a few exceptions. Most of you guys, your passcode will be your lunch ID number. Go ahead and type that in. If that doesn't work, please come up to me and I will tell you your passcode.
Anybody?
Seriously? Okay. Take this one at a time.
Tom's crashing out. Tom's crashing out. Okay, thank you.
CH92.
CH92?
Mm-hmm.
Capital CH? No.
Lowercase. So write that down somewhere. Marcus, you're MF27.
Okay.
Demetria.
Yeah.
That would make sense, huh? AD93.
For what?
But so basically, rainfall not necessarily. Oh, you were off about it.
RV94. Write it down somewhere. Urine.
Thank you for bringing that up. And then, yeah, you get to the stuff. Your partner.
NH59.
Just check, yeah, just check when you're neighbors.
MR30.
30, and please as cool possible.
Yeah.
CW21.
Well, luckily, so
KR56.
my favorite graph.
It's your lunch number. Did you try it? EM40. Lucas. JL65.
Is it all lowercase?
Yeah. FE28. ER43. KE70. Okay. Okay. So hold on. Make sure you write down your passcode. Just write it in front of your notebook. Bookmark. Bookmark. I wouldn't probably bookmark your gizmo itself because that might take you to a weird login. Once you guys are in your gizmos, right now you won't see any simulations. But when Dr. Harris and I add a simulation, or from now on, if I see a simulation that might be helpful, you guys might want to check this. Okay. If you have any questions, please ask me before I leave. By the end of this week, make sure you guys log in.
You're dark. I live. Donnie, you coming or not? Yes, I guess. You really want me to.
Okay.
If you would say. Felix. They got 2 minutes early to lunchtime.
No.
Can we go up?
LQ 32.
Go find a range. You fire that though.
Let's push. Can you push?
What's your name?
Here?
Yeah. And then in for all.